world powered by precision, there exists a material so pure, so stable, that even the slightest imperfection could change the way we see the universe. Today, we take you deep inside the process of creating optical glass and ultra-low expansion. Glass ceramics materials that form the heart of advanced lenses, semiconductor equipment, and even massive space telescopes. This is where science meets craftsmanship. Let's begin. The journey starts with eye-line high homogeneity, optical glass, a material renowned for its extraordinary transparency and uniform refractive index. It's what allows lenses to capture light with incredible accuracy. Used in semiconductor exposure systems and high-precision inspection instruments. The process begins with raw material blending. Silica sand, borax, soda ash, and limestone, the essential ingredients of glass, are carefully weighed and mixed. Around 300 to 400 kilograms of these powders are combined at once. Inside this machine, the ingredients are blended with meticulous precision. Next comes primary melting. The powdered mix is fed into a furnace and heated beyond 1000 degrees Celsius. At this blazing temperature, the materials melt into a glowing, molten liquid, the birth of glass. A large forklift grips the crucible containing this molten glass and pours it onto a tray-shaped mold. This moment, known as casting, transforms liquid into solid form. Within an ore, the glowing mass cools and hardens into glass. But this is only the beginning. The newly formed glass is then crushed into fragments called cullet. Optical glass demands absolute consistency in transparency and refractive index. Its ability to bend light. To fine-tune these qualities, the cullet undergoes a second melting. Measured precisely by an automated weighing system, the cullet is remelted in carefully controlled proportions. This stage, known as secondary melting, determines the final optical properties of the glass. Two types of cullet are blended to reach the exact refractive index needed. The molten glass is then shaped into sheets and cooled slowly over several dozen hours. A deliberate process that prevents cracks and imperfections. Once cooled, the sheets are cut with expert skill. Even a small deviation could ruin a perfect piece. The molded glass then undergoes a detailed inspection. Using cameras, specialists check for stray, subtle variations in refractive index that could distort light. Bright light is shown through the glass to detect bubbles or foreign particles. Only pieces that meet the highest standards move forward. Cylindrical products of precise diameter are cut from these sheets, each destined for specialized optical applications. To further refine the refractive index, the glass is placed inside an electric furnace for annealing, a heat treatment that can last several weeks. The glass is slowly heated and then cooled, allowing atomic structures to settle into perfect uniformity. Even the rate of cooling affects the refractive index, so every moment is carefully monitored. Once annealed, the glass is ground and polished. Both surfaces are flattened with micrometer-level precision. The outer edges are smoothed and shaped to meet exact dimensions. After polishing, the surface is checked for accuracy. Every fraction of a millimeter matters. Each piece undergoes final inspection. Its refractive index, transparency, and surface perfection are tested. Technicians carefully examine every bubble, scratch, and particle. Only flawless glass earns approval. Finally, the finished products are packed using cushioning materials and dedicated trays, then shipped worldwide, ready to become the eyes of machines that shape modern technology. Now, let's move to something even more remarkable. Ultra-low expansion glass. Ceramics, known as Clearis Z, developed by O'Hare. This material achieves zero thermal expansion. In other words, it does not expand or contract even when temperatures change, an innovation made possible through advanced melting and nanocrystallization technologies. It's used in semiconductor equipment and even as mirrors in the world's largest telescopes. The process begins similarly. Raw materials are melted at over 1000 degrees Celsius and poured into massive molds. Technicians closely monitor the temperature, waiting for the perfect moment. Once stabilized, a cover is attached, and the molten glass, weighing several tons, is transported by forklift to the annealing furnace. Cooling is gradual, precise, and critical. Any sudden temperature drop could lead to cracks or distortions. After cooling, the material undergoes a series of inspections. First, a material inspection ensures all physical specifications are met. Next, a pre-crystallization inspection checks for potential flaws that might cause cracking during crystal formation. Then comes crystallization, the defining step. The glass is placed in an electric furnace, where nano-sized crystals begin to form within. These microscopic crystals suppress thermal expansion, giving clear SRAM-Z. Its incredible stability. Once crystallization is complete, the product is inspected under specialized light sources. Dimensions, structure, and clarity are verified with extreme precision. The result, a material so stable and pure that I prefer this response.